the external forces or the pressure forces. Okay, we discussed about only the acceleration velocity changes, and while flowing in this topic we are going to discuss only the directions or the space coordinates, how it is going to change, and we are going to find the velocity and acceleration. So focus is main on the type of flows, okay, type of flows, and on that basis we are going to derive some equations where space coordinates and the time, depending upon the time, how the acceleration and velocity changes. So in this third unit we have three parts. One is fluid kinematics, then fluid dynamics is there, then the fluid flow measurements. So these are the three components. So in that, one of the component is fluid kinematics. So fluid kinematics is very small part in this entire syllabus compared to fluid statics and fluid dynamics. So in this fluid kinematics we discussed Eulerian and Lagrangian approach to understand the fluid in motion. Then we discussed types of flows. Then concept of local and convective acceleration we discussed in the last class and with some problems. Velocity, acceleration of a fluid particle. Then we discussed about continuity equation in the 2D and the 3D dimension, how to derive it, and with some of the examples. So today we'll complete that fluid kinematics parts with remaining problem, one of the remaining problem, which we left in half of the problem we completed, half we left. Then in fluid dynamics we are going to discuss about Euler's equation. See here, Eulerian is different, Euler's equation is different. So Euler's equation in motion with external forces. So in fluid dynamics we are going to discuss the flow of the fluid. The fluid is in flow with some external forces or the change in the pressures. So all those things we are going to discuss. Then we are going to also derive the Bernoulli's equation. So just one step difference between Eulerian and Bernoulli's equation is there. Then we'll discuss about some numericals on the Bernoulli's equation for real fluids or some other fluids. Then the last part of this unit is fluid flow measurements. So this already you have done in the fluid mechanics lab, I think. How to use the venturimeter and orifice meter, or notches if you have done. You might be knowing the triangular notch or the rectangular notch. Using these different notches or the venturimeter, orifice or pitot tips, how we are measuring the flow of the given fluid. So these are the flow measuring instruments. Okay. So here we are going to derive the equations which you are using in the lab. Already in the lab we have used the equations. So those equations, how we came to know, or how we have to find out the discharge or the flow of the fluid. So by using those equations, or that equations we are derived here, that we are using the numericals or in the lab. Then self-study we have in fluid kinematics, that is velocity, potential, stream functions, and numericals on notches. So numericals on notches I'll take one or two. Left all numericals will be like lab, you can refer, or else you can refer some books to solve the problems on notches. Is the audio and video is clear? Okay. So coming to that left out
Yes, sir.
problem. So this PDF file or the notes of third unit, I have combined all the things and I have shared in the classroom. Okay. So here I have combined the PPT as well as handwritten notes for your reference. We came to the last problem. So I think here, correct, we started with this problem, correct? This we have completed, I think, 2TK we have completed. Okay, you can note down this. A fluid flow field is given by, that is a velocity, capital V, in the three directions with magnitude we have given in the vector form, that is x square y into I plus y square z into j minus 2xyz plus yz square into k. So ijk are the directions of given flow in xyz directions, like, and magnitudes given are in algebraic form, that is x square y in x direction, y square z in y direction, 2xyz plus yz square in z direction or the third direction. They have given this velocity in vector form. Prove that it is a case of possible steady incompressible fluid flow. So here one should again recall, for a steady flow, what should be the continuity equation? So in the continuity equation, we are neglecting that dou u by dou t, or change in the velocity with respect to time, will be 0, because we are not going to consider the changes of velocity with respect to time. If the change in velocity with respect to time is 0, that becomes a steady flow. So that we are neglecting the equation, and it should be incompressible fluid flow. So for incompressible fluid flow, we are not recalling the density parameter. So density will be remaining constant throughout the flow. So density we are not going to consider in the continuity equation, or we are not considering the generalized equation for the continuity equation. And from that generalized equation, density parameter and the change of velocity with respect to time, that is dou u by dou t, we are going to neglect. Then we need to find out velocity and acceleration. Calculate the velocity and acceleration at the points. So at what coordinates we need to find out at which given point. Because here, whenever we call about the point, this is the Lagrangian approach, where the fluid particle is considered and analyzed. Yes. So they have given x value 2, y at 1, z at 3. So at this position, we need to find out velocity and acceleration. So now coming to the given values of velocity in xyz direction, they have written as we followed in the earlier problems. X direction velocity small u, that is x square y. V in y direction, they have taken y square z. In z direction, they have considered small w, that is this complete bracket with negative sign. So minus of 2xyz minus yz square. So these all three things they have considered. Now for finding the velocity and acceleration, in the acceleration we need this differentiation of all these values with respect to given coordinates. So once you differentiate them, what will get? X square, we can get it as 2x, because we are differentiating with respect to x for the x direction velocity. So dou u by dou x, you can write 2xy. Then differentiating the second term with respect to y, in y direction, if you differentiate, it will be again 2y into z. Then third term, if you differentiate with respect to z, the third term, if you differentiate with respect to z, what will happen? Z raised to 1 is there here. I can write it as minus 2xy after differentiation, minus, here z square is there. I can write it as 2yz. Okay, like this you can differentiate and keep the terms ready, so that you can substitute directly in the velocity or acceleration, or in the continuity equation also. Now coming to the continuity equation, for a given case, this we need to prove that differentiation of all these three terms and summation of that terms will be 0 for a steady flow and incompressible fluid. So for a steady flow incompressible fluid, after neglecting the density and time factor, we are going to get this equation in 3 dimensions. Dou u by dou x plus dou v by dou y plus dou w by dou z is 0. So once we substitute all these values, we are going to just prove that whether the continuity equation is applicable or not. So once you substitute all these equations, that is dou u by dou x is 2xy plus dou v by dou y is 2yz, then minus dou w by dou z term, that is minus 2xy minus 2yz. If you substitute, you can see here 2xy, 2xy minus 2xy can cancel, 2yz minus last term 2yz you can cancel, it will be 0. So by this we can prove that the flow is, what is that flow? It is a steady and incompressible flow. That is proved. Now after this we need to find out the velocity. So now coming to the procedure to find velocity and acceleration. So velocity, we already know that the given equation itself will denote us the given velocity in the algebraic form. And in that, for a given coordinate, we can substitute x, y, z values, and one can find out the resultant velocity or the total velocity. Okay. And for the acceleration, we need to differentiate the velocity terms. That's the next step. So coming to this velocity step, what we are going to do is, for a given Cartesian coordinate, we have to substitute x equal to 2, y equal to 1, and z equal to 3, which is given in the problem. So just substitute these x, y, z values in this velocity component or the equation, and one can find out what is the velocity in the vector form, and using this vector form, one can find out the resultant velocity at a given position. So here x is 2, I can write it as 2 square into y given as 1 is 1. So 2 square is 4 into 1, 4i. Second term is y square z j. Y square is 1, z is 3. So it will be 3j. I'll get 3j here. Minus last term, if you see, it is 2xyz plus yz square. So I can write it as 2 into 2 into 1 into z value is 3. Okay. Plus y is 1 into z square, that is 3 square. So what I'll get here, 2 into 2, 4, 4 into 3, 12 plus z square is 9, 9 into 1. So 9 plus 12. So finally you can get it as 4i plus 3j minus 21k in the vector form. Now using these numbers, see these numbers are the magnitude. We want the magnitude of velocity. So that I can write it as square root of x square y square plus z square, or velocity in x direction, velocity in y direction, velocity in z direction. That is nothing but small u square, small v square plus small w square. So that value I can substitute and write it as 4 square plus 3 square minus of 21 square. So if you take all this sum and square root, I can get the resultant velocity. So that is coming around 21.587 units. So here units are not mentioned in the problem. Directly you can take the number itself. After this, once the velocity and the coordinates are known to us, now we can go for finding the acceleration at a given same point, that is x at 2, y at 1, and z at 3. So at this position, now we can find out the acceleration. So for that, again recall the acceleration in x, y, z directions. The equation in x direction I'll read, and similarly you can just go through the y and z direction. The next direction, steady flow. See, look at the problem. They're asking only for the steady flow and the compressible flow. Incompressible flow. So in such condition, I can write acceleration in x direction, neglecting that density and neglecting the time factor. I can write it as small u into dou u by dou x plus small v into dou u by dou y plus small w into dou u by dou z. It is all in x direction. Okay. So how the acceleration is behaving, or acceleration is going to change only with respect to space and in x direction only. So this we saw in the derivations or in the steps of finding acceleration, we found it. And similarly for y direction, we are taking dou v as a common term, and we are writing the equation for the acceleration in y direction. Similarly for z direction with w. So substituting these values in the above equations, one can find out the acceleration in xyz direction. Then also he can find out the resultant acceleration. So u value, if you see, u into dou u by dou x, if you want to find out, I know u value which is given in the problem itself. What is that u? X square y. So this we have written here. X square y is u. If you differentiate dou u by dou x, I'll get 2xy. So these two you have to multiply. Then we have to multiply v with 2xy. Then small w with dou u by dou x. So like this we are going to repeat the steps. So see here, u is given x square y, dou u by dou x 2xy. Okay, so this dou u by dou x term is going to remain common in the first acceleration in x direction. Okay, so dou u by dou x we know. Then dou u by dou y we have found out, that is x square. Then dou u by dou z, if you again differentiate, what is dou u by dou z? Here z term is not there in the first equation. Just a minute. Okay. So coming back to the problem. So we need here u, v, w, and differentiation of this u with respect to x, u with respect to y, and u with respect to z. All these things we need to find out. So as the z term is not there in the u equation or u parameters, so we cannot differentiate with respect to z. That will be 0. So that is taken here. Dou u by dou z as 0. Then similarly, for the next term, we need v. So v can be found out as in the given equation y square z. So you cannot differentiate this y square z with respect to x. It will be 0. So dou v by dou x will be 0. Dou v by dou y 2xy z. Already we found out. Then dou v by dou z, if you differentiate with respect to z, it will be y square. So only this is the addition in this acceleration. We need to find out differentiation with remaining two directions, x and y or y and z. Then lastly w. So for this we need to take the w terms from the equation. So from the equation we know that 2xyz plus yz square with minus term is given, which is nothing but the small w. So that is taken here. Now for the velocity, acceleration in the z direction, if you see, we need to differentiate this small w with respect to x, y, z, and also we need to multiply with small u, v, and w, which is given in the problem itself. So now we will try to differentiate with x, y, z. So you can differentiate the first term with all x, y, z, but the second term you cannot differentiate with respect to x. It will be 0. So dou w by dou x, if you see, it will be minus 2yz minus 0. It will be minus 2yz. Next is to differentiate with respect to y. Again, it will be minus 2xz. Here y term is there in the second term. So carefully you have to see the terms which are there. It will be minus z square. Then dou w by dou z. If I differentiate with respect to z, what I can do is, first term there is z term. I can write it as minus 2xy minus, after differentiation of this yz square, I can write it as 2 into yz. So like this we can take all these terms separately and we can substitute in the given above equations. That is, acceleration in x direction can be given as u into dou u by dou x, u into dou u by dou y, plus w into dou u by dou z. Okay, so this dou u by dou z, you have to take all these terms and substitute the values what you found out after the differentiation. So once you substitute with the numbers, because coordinate is also given, so coordinate values are also given 2, 1, 3, x, y, z values. So once you substitute all these values and sum it with the minus sign in the with w, okay. So with these signs, if you substitute and get the values, so acceleration in x direction, the magnitude will be around 28 units. So one of you can please check the values whether they are correct or not, or any rounding off, maybe some problem may be there, or values may be one or two numbers may be difference. One of you can check and tell the answer in the chat box. Then ay, so again ay will be u into dou v by dou x in plus v into dou v by dou y minus, so here plus into bracket you have to write, but after that we will getting minus sign, minus dou w by, sorry, minus w into dou v by dou z. If you take all those terms and substitute the coordinates 2, 1, 3, the acceleration in y direction we are going to get minus 3 units. So similarly follow this equation, acceleration in z direction, that is u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z. If you substitute all these values, the acceleration in z direction will be getting around 123. 123 is the acceleration in z direction. Now finally, by using these three numbers, we can find out the vector form of the acceleration in the magnitude as well as direction. We can write it as
Excuse me.
28i. Yes.
So 123 is in Z direction, right?
Yes. How much you are getting? If you are getting any other answers or any mistakes are there, please find out and let me know. So same procedure of velocity, we can find out the resultant acceleration also using these three values. We can find it as square root of sum of all the squares. 28 square minus 3 square, 123 square. If you add these all values, I can get the acceleration or the total acceleration or the resultant acceleration around 126.18 units. All of you understood the problem? Here only steps are more, but the thing is we should know the differentiation and proper equations. One step differentiation and the equations in which the value should be substituted. So once you know the equations and one step differentiation, anyone can solve this problem. So once you have followed this, you just inform me. We'll proceed to the next part. Acceleration in Z 63 watt. Check these values in AZ. AZ is U is x square y, U value. So carefully once again observe the substitution. X square y is U, okay, into bracket dou W by dou X. Dou W by dou X after differentiation of this W term with dou W by dou X, I got minus 2YZ. So this U term x square y I'll multiply with minus 2YZ. So they have taken this term plus V into V is given in the problem y square Z here, okay, y square Z into dou W by dou Y, means we need to differentiate small w value with respect to y. Here AZ V into dou W by dou Y. So dou W by dou Y minus 2xz, you have taken correctly, minus y square z, okay, v value, dou W by dou Y. Dou W by dou Y is here, minus 2xz minus z square, minus 2xz minus z square. Yes, correct. Then last we need to take small w into dou W by dou Z. Dou W by dou Z is minus 2xy minus 2yz. W is given in the problem, that is minus of 2xyz plus yz square, or you can write it as minus 2xyz minus yz square. So see the last term. Last term is minus 2xyz plus yz square is the given term in the equation, in the main equation, into bracket minus 2xy minus 2yz. So carefully take these signs, then substitute all these numbers. With respect to x you substitute 2, in place of y you substitute 1, in z you substitute 3, and find out acceleration in z direction. Then they have taken minus 2x square y square z minus 2xy square z square minus y square z cube plus 4x square y square z plus 2xy square z. I think here they have made a mistake, I think, in this term. 2xy square z square they have taken. It should be z. 4xy square z square xy square z square is plus 2y square z cube. According to this first equation, in this only substitute all these xyz numbers and find the acceleration in the z direction. Whether we are getting 63 only, 39. Okay, Sunita, how much you got now? Acceleration in z direction. Is it 123, 63 or 39? 39. Okay. What about others? So there may be printing errors or some other errors while solving these problems. So results may be different. So please all of you confirm the results in the given PDF files. Okay, is it 39? We'll consider all of you. So if you consider 39, then just check this acceleration, resultant acceleration, how much it will be. 28 square minus 3 square plus 39 square and square root. .10. Others are getting the same answer. 48. Okay, 48.1. So all of you be clear with the steps what they followed and what it should be as per these given standard equations. Okay. The formulas which we found out by the derivation, and after deriving and substituting these values, what should be written in these steps, that should be very clear. If any one value is not taken or any square is not considered, signs are not considered, then value will be wrong. So please confirm this acceleration in z direction and the resultant acceleration. So if all are agreeing with this number 48.10, we'll consider that result. Okay, so make it small change there. So for this given problem in the notes, problem number 5.8. So all of you remember this problem number 5.8. Resultant acceleration is coming around 48.10. Okay, as per the other results. Okay. Shall we move to the next slide? If any others have found out the calculation, can just answer here in the chat box. If any other results, 48.10 also not correct, or given result in this also it's not correct, then you can reply in the chat box. Okay. The next slide I will just show here. You just find out the results whether they are correct or not. Okay, you follow the procedure. You understand the given problem. So whether the all steps have been properly used and all the substitution is correct or not, you check the last slide. It's like a classwork. Okay, so take 1 or 2 minutes. Within that, you just tell me the given problem is right or wrong. So take this problem. It's again going back to the basics, finding one of the unknown. See, others also should follow this. Please note down the problem, go by the continuity equation steps, and here we need to just find out the unknown term, unknown equation for x direction velocity. Velocity in y direction is given, velocity in z direction is given, velocity in x direction is not given. That we need to find out by using the standard continuity equation. And in these such cases, we cannot consider again dou u by dou t also, because time is not known. And also, if you consider density is also not given in the problem. So we can assume the flow may be incompressible and steady, so that we can get only these three terms: dou u by dou x plus dou u by dou y plus dou w by dou z equal to 0. You can substitute all these values in the given equation, and we can find out the unknown value of velocity in x direction in xyz terms. If anyone found out, can reply in the chat box or can tell in by unmuting the mic.
U equals to 2x square plus 2yx sir.
1 minute. Yes, what happened? Four x square plus 2yx plus c. Okay, good. Two x square plus 2yx plus c. Yes, Ashish, you got correct.
Y.
Sir, I got sir.
Okay. Yes, another student is telling something. The voice is not clear. See, I think Sunita or Pushpa.
So I said answer.
Answer is correct.
Yes.
Okay. So keeping here one of the unknown, that is dou u by dou x is unknown. You can differentiate v term and w term, and you can just find out the unknown term dou u by dou x. Then you have to integrate, because here already it is in differentiation form. That is 4x plus 2y, with differentiation term you are getting. You can find out integrating. So one step, if you integrate, you can get it as 2x square plus 2xy plus c. Okay. So c may be 0 also here, or it can be neglected constant. Okay, this completes the fluid kinematics parts, and in this self-study part is you have to refer that is velocity, potential, and stream functions. So that thing is self-study. You can just read the theory part, and if any small problems will be there, that you can refer. Okay. Now we'll come to the very major part of this syllabus is the fluid dynamics. Okay, we'll take a break here. The time is around 10:44. So after break at 11, we'll join the class, or we'll continue. You start the class. Okay, coming to the next part of the unit 3, that is the fluid dynamics. So in this part, we are going to study about the fluid in the motion. So in the lab, we might have observed the fluid is flowing in pipe. The fluid is flowing in open channels with V notch. Okay, or the fluid may be flowing in a given proper dimensions like a channel. If you take a channel like rectangular, it may be a trapezoidal channel, or it may be a triangular channel for a standard geometry. But if you take a reverse where the water is naturally flowing without any proper cross sections, where the cross section is continuously changing with respect to the change in direction or change in length of the river. Okay, so these kind of flow of fluid with some external forces or the forces which are applied on the fluid which causes the flow, that we are going to discuss in this fluid dynamics topic. So here, before going to the type of equations we are using or the forces which are applied on the fluid, we need to discuss about on which law it is going to behave, or on which law it is going to flow. So primarily it is going to behave as per the Newton's second law of motion. So that states that the rate of change of momentum is proportional to the applied force. Okay, so any changes in the movement of the fluid is there, it is with respect to applied force, and it is in the same direction also of the applied force. So whenever you apply some force on the fluid also, like solid material or other materials, fluid also behaves in the same direction. So by using this Newton's second law of motion, we are going to analyze the different forces which are applied on the given fluid. So that is our basic equation on which we are going to discuss the fluid. The next, what are the various forces which may be applied on the fluid, or in the fluid also some of the forces may be generated due to which it is going to flow or it is going to move. So any change in the position or in the movement of the fluid you observe, that all comes under fluid dynamics. And whenever you focus the fluid which is in stagnant or which is not in motion, such conditions you have to analyze by using fluid statics. And whenever you are just analyzing the directions or just the velocity and acceleration or the type of flow, then you have to consider it with the fluid kinematics. So now in this chapter, we are going to talk about the forces. So we have to always focus on the forces in this fluid dynamics topic. So coming to the various types of forces which are applied on the fluid or from the fluids or from the different fluids which are interacting, those all forces are listed here. Any issue with the network? Audio, video, any issues are there? Okay. Okay, thank you. So coming to the various types of forces which are applied on the fluid, anyone can recall again these pressures or the forces. So one is force due to pressure applied on the fluid, due to which it is flowing. That is one force is pressure force. So force exerted on a given area of the fluid, we can call it as a pressure. And because of this, the fluid is going to move. So you can recall the pump or a blower, you can recall. So blower is going to increase the velocity of the flow of the air. So similarly for fluid also, a pump is going to pressurize the liquid in a given pipeline, in an enclosed channel. So here the exerted or the force exerted on the fluid mass, if there exists a pressure gradient, so if any pressure difference is there, then only it is going to flow. So to create this pressure difference, we need, for liquid we need pump, for air or the gases we need blower, okay, which are power consuming and pressure producing or the force producing devices. So such type of devices will generate a pressure difference here or a pressure gradient. If there is no pressure gradient, then the force cannot be applied or there is no difference in force. Then a body cannot move. That's the same, the simple concept. So whenever there is a pressure gradient generated between 2 points, then the flow can be generated. And that will be in the direction of the given difference. So in which side the pressure will be high, from that position to the low pressure point, the flow is going to take place. Similarly, here we know the gravitational force. So gravitational force is also acting for all the bodies on the earth. So earth is having its own gravitational force constant, and according to that, all the bodies are going to behave to move in different directions from top to bottom or from high head to low head. Okay. So like that, due to weight of the fluid itself, it is also having some gravitational force, and by this what will happen, the movement of the fluid is going to take place from the high head to low heads. Similarly, we have viscous force. So this also we discussed in the fluid statics while discussing the fluid properties. So viscous force is what? The resistance between the two fluids, what we discussed. That resistance or the coefficient of viscosity mu, what we discussed, that itself is nothing but the viscous force, due to which the fluids are going to reduce its velocity or reduce its motions, or because of the high speed fluid which is interacting with the low speed fluid, then what will happen? The low speed fluid will take its speed of the other fluid and it can also move in a higher speeds. So like this, the fluid which are flowing with some viscosity like water or if any other oils if you consider, these all forces, because of the interaction of fluids or the resistance between the fluids, what the forces are generated, that we are calling it as viscous forces. So this exists in real fluids due to viscosity. So that is denoted by Fv. So you can see the notation of these forces. What is denoted by Fp is pressure force. Fg is the gravitational force here. Then one more force we discussed about the viscous force. That is Fv. Then due to change of type of flow, which we discussed in the Reynolds number or the turbulent or laminar flow. Okay, in that, if the fluid is moving above some high speeds and some turbulence is created in between the fluid particles, or there may be exchange of forces with high speed fluid particle with the low speed fluid particle, or between the same fluid also. In this turbulency, the forces which are exchanged, such type of forces we are calling it as turbulent force. So when the fluid particle moving from one layer to other layer also, or in mixing conditions, or in very high drastic change in the speeds, so there will be exchange of forces between the two fluids continuously, and it should be in turbulent, where the Reynolds number should be more than 4000. Such type of flow in mixing conditions or the where the layer formation is not possible. So all the fluid particles are continuously moving each other in independent directions with high speed. Such conditions, we are considering there is a turbulent force is generated. Okay, where the fluid particles are moving from one layer to other layer with additional movements or the stress which are generated. So such forces we are considering it as turbulent force. So that is denoted by Ft. Then in the statics also we discussed about the surface tension force. So surface tension force we discussed only for the surface of the liquid. So for any liquid, if you consider the surface, there will be always a surface tension created, like a layer. So to disturb that layer, we need to apply some force. Then only a body or a surface can move inside the fluid. Until that, because of this surface tension force or the cohesion forces between the liquids, the surface tension force will be more. So due to that force, the mixing of the fluid is also not possible some cases. So that force we are denoting it by Fs. Okay, that is one of the force which is on the surface of the liquid, not for the given depth. If the depth of the liquid is more, we are going to assume this surface tension is 0. Or for a very high depth of water, where the surface is less but the depth is more, in such cases we are assuming the surface tension force is not uh, available at the surface of the water or the liquids. And also it is always very small compared to all other forces. This will be always very small. Then other than this, we have compressibility forces. Okay, so these forces are due to the elasticity property of the fluids. So some fluids will be having some elastic properties. So whichever fluid is going to release or retain its positions, then it is going to transfer some small forces between the molecules to retain its own position. So in such cases, these forces are also considered. So like this, we have very different types of forces. Okay, so those forces which are responsible for creating any flow of the fluid, such forces are also responsible to create the motion, or with the forces which are responsible to stop the fluid also. These forces are responsible for creating some dynamics in the fluid. So considering these forces, we are going to analyze some derivations, which we are going to consider some assumptions again, and we are going to derive some of the equations which are useful for our numerical solutions. Next, coming to the types of equations. Now we need to find out different equations for these different forces. If you take the force, what is available in the fluid with respect to Newton's law of motion, so that force may be due to pressure force, or it may be gravitational force, or it may be viscous force, or it may be any type. And if you take the real fluids in real applications, okay, in such conditions we need to take all the forces which are responsible for the flow of the fluids. So that is written in the bottom side here. So if we consider all the forces which are responsible for the fluid movement, like for the real fluids, in the real fluids we are not going to assume any forces which are negligible. In such cases, we can write it as sum of all the forces, that is pressure force, gravitational force, viscous force, turbulent force, surface tension force, and the compressibility force. So due to these all forces which are added here, due to which the fluid is going to move, and that fluid is going to move in the direction of force applied only. That's why we can consider that force applied in a given direction, or the net force, can be mass into acceleration provided. Okay, so this mass into acceleration we have taken from second law of Newton's. So you can substitute that force of fluid as m into a, and we can find out these all the forces. If the forces are known, we can find out acceleration of the mass of the given fluid. Now next is for some cases. So again we started with the assumptions. Now we start with the assumptions, and we have to come to some simplified forms, because many forces are very negligible in some conditions, or in some problems they may give some ideal fluids, or it may be a different fluid with different conditions. In such cases, we need to consider the simplified form of this equation. So such forms of equation, if you consider, the first condition, if you neglect the surface tension, okay, the surface tension and the compressibility of the flow, that is nothing but the cohesion forces and the compressible elastic forces. If you neglect, then we can write it as the flow of the forces of the fluid available, that is due to only the pressure force, the gravitational force, viscous force, and the turbulent force, not by the surface tension or the compressibility. So if you neglect this surface tension and the compressibility of the given fluids, then in fluid dynamics, for such type of equations, we are calling it as Reynolds equation of motion. Please remember the type of the equation. It is not the Reynolds equation. It is Reynolds equation for a given motion of the fluid. So Reynolds, it is used many times, but you in this chapter you remember that for in motion, if you neglect surface tension and the force due to compressibility, if you neglect, then such type of equation is called as Reynolds equation for motion. That is considered with neglecting surface tension or force due to surface tension and force due to compressibility. Means we are not considering the cohesive forces of the fluid. So that equation is called as Reynolds equation of motion. Next, again, we are going to neglect turbulency and other forces. So in further, if you neglect the turbulent force, okay, then what will be left now? The force generated in the liquid, that is m into a, can be equated to pressure force, gravitational force, and viscous force. So this type of equation, where we have neglected turbulency, where we have neglected the surface tension, and also the compressibility force. So if you neglect all those three, and if you consider only first three terms of force, then that equation is called as Navier-Stokes equation. This equation is very important for your aeronautical field. This Navier-Stokes equation. So this is the generalized equation. In detail, you are going to study in CFD or any other subjects, okay, of your aeronautical subject. So this is going to be used in many applications, Navier-Stokes equations, where the fluid is moving on the given bodies, or the body may be moving by considering the fluid in stagnant condition. In such cases, we are going to discuss about this Navier-Stokes equations, or in a combination of heat transfer of the fluids or the fluid dynamics. There also we are going to discuss about this Navier-Stokes equation. This is very important for your different subjects. Okay. Next is, if you also neglect this viscous force. Okay. So this viscosity, if you neglect with all other turbulent or surface tension or the compressible forces, then that equation becomes the ideal equation for the ideal fluids. So by moving one more step ahead, that if you consider only the first two terms, that is, the fluid in motion is possible only by pressure force and the gravitational force, that which we consider in lab also. So those forces are the pressure force and the gravitational force. And neglecting all these remaining forces with viscosity, surface tension, uh, turbulency, and the compressibility, if you neglect, then that equation is called as Euler's equation of motion. So please all of you note down these three equations of motion. One is Reynolds equation of motion, which is very near to reality. This is the reality where all the forces are acting on the fluids. Okay, because of this, it is having some motion. This is very little near to the reality, that is called as Reynolds equation. Then the equations which we are assuming to solve some of the standard models of the given problems, we are using many times the Euler's equation of motion for fluid dynamics. In the CFD or some other interaction of the different fluids, okay, different fluids are interacting, or a fluid with some heat exchange or some other processes are going to take place. In such conditions, we are going to use this Navier-Stokes equation. Okay, shall we continue? Now, by using this only the Euler's equation in our fluid dynamics, we are going to discuss the or derive the equation for Euler's equation. See, in this equation only, we are just going to analyze this. What is the force due to pressure and force due to gravity? Only these two we are going to consider, and we are going to analyze the Euler's equation in detail. And later, after integrating the given equation, we are going to find out the Bernoulli's equation. So these two equations we are going to consider in this fluid dynamics topic. Okay. Later in the advanced topics we are going to discuss in different subjects. We may be discussing in Navier-Stokes equation or the Reynolds equations in the future, not in this subject. Okay, now coming to the Euler's equation. So this Euler's equation of motion states that in an ideal incompressible fluid, because we are not considering compressibility, surface tension, or the viscous forces or the turbulent forces. That's why in ideal condition, okay, states that in an ideal incompressible fluid or like water substance, in ideal incompressible fluid, when the flow is steady and continuous, the sum of the velocity head, pressure head, and the datum head along a streamline is constant. So this is definition given by the Eulers. It states that whenever a fluid is in motion, okay, all of you assume in mind that fluid is in motion in a river. Don't take any standard shapes because it will be difficult to assume also. Just saw a river, a fluid is continuously flowing. And assume that fluid. Okay, with respect to fluid only, you assume that it is an ideal fluid, means there is no viscosity present. Viscosity is neglected, compressibility is neglected, and the flow is steady and continuous. Okay, for a given time, for this day, if there is no dam opening or there is no rain happening, then we assume that in a river the water flow is constant and it is steady for a given time of range. And in such conditions, okay, without addition of flow or without taking out the water from the river, and if it is not if it is incompressible like water, only it is flowing, and if it is ideal, viscosity is also not there. In that condition, what is the result of forces? There, we are going to consider the sum of velocity head, pressure head, and datum head. So this we are going to derive it in the given derivation, or after derivation also you can define it. So what he defined? The water head due to velocity, water head due to pressure, water head due to datum lines. Datum lines means the water may be falling from the mountain to the ground. That we can call it as datum head, because the ground surface we can consider datum, and if the water is flowing from the top to bottom, then it is called as a datum head. Due to that also flow is possible. Due to pressure, in a given same datum line or the same level, if the pressures are different, then also it will flow, because the pump you can see in a given same line of the pipe without any head difference, the pump can also pressurize the water to flow in one direction to other direction, the same level. And one more is the velocity difference. Within in flow also, if the velocity changes are there, that also creates some head, which is responsible for generating the motion of the fluid. So like this, we are talking about three heads, that is velocity head, pressure head, and datum head, due to which a flow is possible, which is along a streamline. Streamline means for a given passage, it will follow the passage. Like in river, if you see the passage, always the river first follow the passage. When the quantity of liquid overflows, what will happen? It will not follow any streamline. So here also we are following only the streamline. But the condition like a flood condition and other things, we are not following this. So in flood condition means we are taking the viscous condition, turbulency, everything, reality. But here, after these all assumptions, the water will follow the streamline. Like in the pipe means only in the pipe it will flow. If a channel is given, only in the channel it will flow. That is called a streamlined flow. So that will be constant. The sum of these all terms will be a constant. So for derivation, so all the list of derivations, assumptions also given for the derivation. This already we discussed. You can just go through by these points. So all these 5 points are already discussed here. Only one more addition is the flow is irrotational, or the fluid particles are irrotational. That is one of the means you have to assume everything neglected. Only pressure force and the force due to gravity is considered for our ideal conditions. So before going to derivation, first we need to consider one of the fluid element or the fluid particle. So here in this derivation we have considered fluid in a cylindrical form. Okay, in a cylindrical form, a fluid particle is considered in sketch 1. On the right side you can see. Just to zoom it. Yes. Here. So this sketch you can observe here. Flow is taking place in this streamline. The arrow mark you can see. Curve you can see. Like a S shape. This is the streamline or a given passage or the path of the fluid particle, which is moving from this P to outside P. Like this it is moving. Now in this, as per the definition of Euler's or the how the Euler defined or derived this equation, according to him, he considered a datum line here. A datum or a reference line. With this reference line, he took the distance between this pressure point P or the inlet of the flow. If you see in this cylindrical passage, this inlet side, the datum line or the level difference between this inlet side to the datum line, he has considered the height of Z. And as for small element, length of ds, okay, the length of ds he has considered. For this difference between the heads of inlet side and the outlet side, he has taken dz as the change in the level. There is a change in level. So this height is dz, small change in height dz, and the head change between the inlet side of the fluid particle, entry side, and to the datum line, he has taken z. And total weight or a small weight, if you see the weight of this fluid particle, total weight of the fluid particle, all of you know, yes, and the small change of weight or the weight of the small element of this fluid particle, what is considered for the derivation, that he has taken rho g dA into ds. Okay, so recall the weight, how to find out for a given liquid from that equation. Here for the change in weight or the small weight dw, we can write it as rho g, density into gravitational force, area of the cross section of this fluid particle, we can write it as dA, and given length of this fluid element, that is nothing but volume only, rho gv only. So rho gv is recalled in other terms, the cross section area dA, length is ds. So this becomes small weight of the small fluid particle, which is acting downside because of the gravitational force. As we told, in Euler's equation, we are considering only the force due to gravity. That force due to gravity is force due to weight, which is acting in the downside direction. And in the direction of this fluid path, we have taken one tangential line. So with this tangential line, it is making the angle theta. Okay, so this is required to consider in which direction the flow is taking place. According to that direction, how the weight is going to act. If the fluid is flowing in vertical direction, then weight will be rho g dA ds. If it is flowing in different directions other than vertical line, then we need to consider some cos or sine or tan. That depends on the given conditions. Is that clear? Now after this, See here, flow is taking place in the given direction. It is flowing from the downside to upside direction. Now, here we are going to assume some pressure is opposing it, because fluid always should overcome some pressure or should overcome some pressure forces. Then it can flow smoothly in a given direction. So that overcoming pressure, whatever is applied on the other direction, is considered as P plus small change in the pressure due to this change in length, that is dP. I hope all of you understood the sketch, how it is drawn, how these all parameters are considered as per the Euler's equation, where we need to consider the pressure forces. Inlet side it is P, outlet side it has to overcome the extra pressure from the outside. So that is dP is added here, extra pressure, what is opposing. One more force is the gravitational force due to weight, that is rho g dA ds. Only these two forces we have considered, and in which direction it is flowing or what exactly force generated, that is also we can write it as mass into acceleration also by the Newton's law. So that mass into acceleration or the force applied on the fluid, we can write it as sum of all these pressure forces and the gravitational forces. Also for the reference, this theta is analyzed here in this sketch. So as per the sketch, I told you theta for considering full length of the fluid particle, that is full length ds. If you take vertically, it is acting downside here. Vertically, it is acting downside. Fluid passage is in the tangential line ds. Okay, the tangential length if you take, that is ds to the fluid particle. The level difference between exit and the entry of the fluid particle is considered dz. Now one can find out by knowing this adjacent and the hypotenuse lengths, one can find out this theta in terms of cos theta, because we know the hypotenuse and the adjacent. I can write it as cos theta as dz by ds. If you want to find out in the derivation or in the numerical, if you want to find out ds, I can write it in terms of cos theta dz. Or if you want to find out dz itself, or the length of level difference or the head difference, also you can write it as ds into cos theta. So this will be useful in the derivation or numericals. Sketches, all of you understood? Okay, now we'll see how to go by the steps. So again, here we need to add, as per the Euler's equation, we need to add the total pressure forces at inlet outlet plus this gravitational force equal to total force. So here the forces acting or tending to accelerate the fluid element in the given streamline are: one is the net forces due to pressure. You can see here we have considered the flow in given direction from downside to upside. So in that direction, if you see the pressure forces, P is in the same direction, we can consider positive. Other force P plus dP, which is the opposing force on the other fluid particle. Okay, that is considered as minus P plus dP into dA, because these pressures are acting on the given surface area at the inlet and outlet side. So to keep the same area, we have considered one cylindrical area. It may be any area, not only cylindrical. Just for reference, we have taken cylindrical area. So dA is considered with pressure. That becomes force. So force acting at the inlet side is PdA in the same direction, positive. Other force is acting in opposite direction. So we have taken pressure P plus dP into dA, which is opposing. That's why it is minus. So effectively, I can cancel P dA both sides. and minus dP into dA will be left as the pressure force what is acting in the given direction of flow. The next is weight of the fluid element. So weight of the fluid element, if you see, here we have taken dW as rho g dA ds, but this will be acting always in the downside direction towards the earth or towards the ground or towards the given datum line. So according to the given flow direction, flow is taking place from down to top, but weight is moving downside. So it will be opposing the flow. To show that how the forces are also opposing in the fluid flow, we are taking this weight and the outside forces in the opposite direction. So I can write the force due to weight or the gravitational force is given by minus rho g dA ds. Okay, and with respect to fluid element, if you see, with respect to gravitational force of earth, if I see, it is positive rho g dA ds. But with respect to fluid element, if you see the flow of the fluid element, it is flowing in this ds direction. Is that clear? It is making some angle theta here with respect to weight. So that I can write it as dA ds into cos theta, because that is not complete weight of the fluid acting downside. It is acting in a tangential line. It is acting in the streamline of the flow. So that component of the weight is rho g dA ds cos theta, which is acting downside. That's why I have taken negative sign. Is that clear? So now from analyzing that triangle with respect to theta, ds and dz, I can also write that cos theta as dz by ds. So this you have seen here in this case. dz by ds is the cos theta value. You can write it as minus rho g dA ds dz by ds in place of cos theta. So what will happen now? ds can be cancelled. So we left with the simplified form, that is rho g dA dz. ds is cancelled. So in this term, rho into volume, actually rho into volume, if you see, that is nothing but the mass. Mass, if you multiply with g, it becomes weight. This already we know in the fluid properties. Okay, so this ds term is removed here. No, ds term is not present in this weight component. But separately, if you want to find the mass, that will be rho dA ds. The next is acceleration of the fluid element, because on the left side we want to write the force, total force or the net force in terms of Newton's second law, mass into acceleration. There we need to write the acceleration term in terms of this given sketch. So as per the sketch, if you see, velocity, the acceleration is change of velocity with respect to change in time. That everyone knows, dv by dt. And by chain rule, we can write it as dv by ds into ds by dt without changing any results of the derivations, okay, or the differentiation. What we are doing, we are writing it as dv by ds into ds by dt. Nothing but the change in velocity with respect to change in the particle length ds, or the change of particle length with respect to change in time. Okay, that also we can write it. So taking these terms in the chain form, one can write the acceleration as v into dv by ds by considering ds by dt as velocity. Change in distance with respect to change in time. One can consider velocity, and small dv by ds remains as it is. Change of velocity with respect to change in distance, we are keeping as it is. It is like dv by dx only. in earlier cases. So acceleration can be written as capital V into dV by ds. Now analyzing these all terms differently. Why? Because we need mass of the fluid element, acceleration of the fluid element on the left side for the Newton's law of motion. This we are going to equate on the right side with the Euler's equation. That Euler's equation is what? The sum of pressure force and gravitational force. That's why in these 4 steps, if you see, I have written all those things. I have taken the mass of the fluid element independently. Mass is what? Rho into volume. What is volume? Cross-section area into length is the volume. So that we have taken for the mass. Acceleration, we have taken change of velocity with respect to change in time. So change of velocity with respect to time with respect to sketch, what is given in this problem. Okay, with respect to sketch, if I write the change in velocity with respect to time, I can also write with some change with the distance also. The distance is ds. So they have taken chain rule of differentiation. They have written it as dv by ds into ds by dt. Value is not changing, only we are changing the terms. So this ds by dt is nothing but the velocity into dv by ds will be remained with acceleration. So this completes left side of the equation. Right side of the equation, we need sum of this net force due to pressure, that is minus dp dA, plus weight of the fluid component which is acting in downside direction, that we have taken in simplified form rho g dA dz. So all of you, I hope, understood the 4 terms, why we are writing in 4 steps and why it is important in the next step. Okay, we'll repeat sketch also, or only steps, or from starting of the derivation. Okay, only steps. Okay, only steps means you can see here what we need is we need the total force applied to the given fluid, okay, in terms of pressure force and gravitational force. And from Newton's second law, we may also require, to simplify the equation in the future, we may also require mass into acceleration. So keeping this in mind, or from this equation, the above equation, F equal to ma equal to pressure due to force due to pressure, force due to gravity, Euler's equation of motion. For this, what we need is these terms. So first, what is required? We can find out the weight of the liquid element. So weight of the liquid element is what? Density into gravity into volume. So density of the given liquid may be water. You assume water is given. G is the gravitational force. dA is the area of the cylindrical surface. It may be any shape. Cylindrical surface you have considered, you can take dA. Because many times we assume a fluid is flowing in a pipe, cylindrical pipe. It may be flowing in river also, it may be flowing in a channel also, anywhere. But everywhere we cannot consider the proper given area. So we are assuming some area, dA. ds is the length of flow in which we are going to consider that particle. So considered particle here is up to length of ds. So length into area, if you take, it is volume. Rho gv is the weight of the given fluid, which is acting opposite to the direction of the flow, downside direction. And pressure forces, if you see, Due to some pressure only the flow is taking place. Which force? Due to pressure force. So that pressure is applied from the bottom side, that we consider as P. It may be more or less, we don't know. So that P is applied on the bottom side. Whatever the pressure is applied on any fluid particle, if it is incompressible, same pressure is applied on the other side, Pascal's law, or the hydraulic jacks or the JCB, you can see whatever the force is or pressure is applied on one side, without compressing the fluid, the fluid will transfer the same pressure on the other side also. That is P. Plus dP is what? The resistance due to other fluid particles which are on the top side, or that pressure force may be due to the circular pipe which is opposing the flow also. Is that clear? So initially you have to assume the fluid is in stagnation condition. Once you apply the pressure, it will start moving. So to apply this pressure, you have to overcome this extra force also. That is denoted by P plus dP. So if you simplify, I can write it as minus dP dA, effective pressure force in the given direction, if you see. And weight, you can see it is acting downside. So this weight of the fluid particle, here we have taken direction as a vertical direction. But in the direction of flow, if you are talking, in the direction of the flow only we are writing the equation. In that direction, if you see, it is acting at an angle theta. So to consider that angle theta, we have taken this triangle, ds, dz and theta. And according to this triangle, we know hypotenuse and adjacent line. Then I can write it as cos theta. That is minus downside direction. In the flow direction, if you write rho g dA dz is the weight of the liquid. In the flow direction, it is cos theta. In vertical direction, it is only dA dz, ds, not with cos theta. Okay, that is weight. Mass is what? Mass is just divide that above equation by g. Without gravitational force, if you consider, that becomes a mass. Mass is rho into v. So rho into dA ds. Here we are not focusing on the triangle because it is the mass generally taken, okay, not with the direction. That's why gravitational force is not considered in the mass. Then acceleration. Acceleration, you know, change of velocity with respect to change of time. So this is just split up. It is written with respect to some distance. So distance is known for the fluid particle, that is ds. So if you just write in split up form, I can write it as dv by ds into ds by dt. What is velocity? Velocity is change in distance with respect to change in time. So I can replace this ds by dt in simplified form, that is v. dv by dt, we will keep it as it is. So the dv by ds we are going to keep as it is. dv by dt, if it is there, it is acceleration only. But dv by ds is what? Change of velocity in space. Change of distance is in time. So change of velocity with respect to distance, we are keeping as it is. So we can write acceleration as v into dv by ds. Now it is clear? Okay, we'll stop this class today. Next class we'll complete the derivation and we'll also derive the equation for Bernoulli's equation, and we'll take some problems. Okay, and after those problems we'll go for the flow measurement. Okay, thank you.